seated posture measurement software. And these are contents of my presentation. And first of all, first, I'd like to introduce the software. And next, let me introduce the version of the software. That's an example of clinical application. And first of all, if you have questions, you can, but please use English. I'm not so good at speaking in English. If you ask me hard English, it makes me not good. Please speak slowly and please use English. And if you ask me in Japanese, about the software. In the ISO 164.0-1 standard, the representation of seated posture is defined. The parameter is not. So it is hard to apply in a clinical setting. And we have conducted research into method of measuring seated posture. And finally, we developed two-dimensional image analysis software proprietary for seated posture measurement according to ISO. And here is the interface screen of the software which we developed. Let me introduce how to use it. And first, take pictures by digital camera. Next, point to measurement point, it means landmark. Point to landmarks. And then here is calculate button. And push this button. Then angles are shown. This angle shows and body segment line. And then measurement point is hidden. Parts that extend the measurement point outward are used. Here is the bar. And to measure with low error, you can zoom out the picture. We name this the zooming function. To measure with low error too, we name it the function, and click practice function. And here is the software keyboard. And if you push this button, cursor moves one pixel by one pixel. Left up, right up, left down. So you can push and you can identify the landmarks more correctly. And the software name is RESIS. It's two-dimensional image analysis software. Seated posture can be measured according to ISO. And hidden measurement points can be measured and on the PC, digital camera, with travel, and parts are needed. Easily handled and precisely. And let me introduce the results of evaluation of the software. First, we did pointing accuracy experiment. So we wonder people can point what they want. So we did this experiment. Objects are one accelerated targets in the software. Here are 0-5 targets. And subjects are 3 men. And they point these objects and use desktop PC and notebook PC. And 3 times repeated each. And the result is that by using click assist function, 100% correctly pointed. accuracy experiment. I'm sorry. Result of pointing accuracy experiment, the quick assist function needed to be used. Next, we did the distribution experiment. Pictures taken by camera had distribution like that. It was error measure. Here is an image of distribution. Distortion. Here is no distortion picture. Here is pattern view shape distortion. Here is barrel shape distortion. These pictures may occur error in measurement. So this distribution distribution and zooming magnification of digital camera is related to each other. So we calculated the relationship between the distortion and zooming magnification of digital camera. X-axis is zooming magnification of camera. Y-axis is largeness of distortion. So here shows large distortion. Here shows relatively large distortion. About 2 times of zooming magnification. Here is lower distortion area. The result of the distortion experiment is that pictures should be taken with about 2 times zooming magnification. And next, we did repeatability experiment. We made a mental model, and we make it an object. And this mental model representing sitting posture. And subject is 32 years old man, and subjects are 2 men and 1 woman. And 3 times repeated for each measurement line. The results are here. Largest value and mean value of standard deviation of each experiment is here. Here is used bars, measurement with using bar, and here is not using bar. And we need the result of using examiner experiment, and here is inter-examiner experiment. And max value and average value of standard deviation is here. So, result of this experiment and standard deviation are less than 2.8 degrees. And we conclude that software which we developed is practical and suitable for daily clinical use. And last, we did validity experiments. And we compared the software with the 3-dimensional measurement device spin arm. I'm sorry, and this is not Paro. And object is meta model, and subject is 32 years old man, 3 times speed. Result of each measurement lines are here. Here is the result of measuring by software, and here is by the device. Differences of mean value is here. So, result of variety experiment, differences between software and the 3-dimensional measurement device are less than 4.8 degrees. And we conclude the software which we developed is practical and suitable for daily clinical use. I think to measure meta model is more easy than the measuring this result. Here is, for example, very differences of very triangle compound. Abdominal line and neckline and headline is very low differences, but trunk line and sternum line shows relatively large differences. We thought why the result is. Here is orthogonal projection, but taking pictures by camera is not orthogonal projection accurately. So this occurs error. The farther the camera to object distance, the more concrete the result of measurement is, because the farther the camera to object distance, it's gone. It near to project orthogonal projection. So this is relatively low error. Last, we distributed quizzes as free software. If you want quiz access,